Yeah, welcome to today's lecture. Last time I defined the so-called wave operators, omega plus minus AB, in the context of scattering theory, which were defined as the strong limits for t to plus and minus infinity, exponential I ta, exponential minus I tb, and here we also had the projection onto the absolutely continuous subspace with respect to the operator B. Yeah, here of course A and B are self-adjoint operators on some Hilbert space H, which has the decomposition into a pure point space, an absolutely continuous subspace and a singularly continuous part. This decomposition holds true for a self-adjoint operator. It's always with respect to a certain operator. And here we have the projection onto this HAC space for the decomposition belonging to the operator B. We also defined last time in definition 3.7, which I would like to recall, what completeness means. We said that the wave operators are called weakly complete or weakly asymptotically complete. If the following is satisfied, if H in is equal to H out, and here we had, I should recall this too, H in or sometimes H minus, this was the range of omega minus, and we had H out, or sometimes I will also write H plus for the range of omega plus. Yeah, exactly. Okay, and we say that the wave operators are weakly asymptotically complete if this here holds true, if we have this equality. We also said that in number 2, the wave operators are asymptotically complete if H in equals H out, and they both are equal to the orthogonal complement of HPP with respect to the operator A. And finally, which is the most important definition and which I will use in the following, we say that the wave operators are complete if H in is equal to H out is equal to H AC of A. Here I would like to go on with the following remark. This is remark 3.8. First of all, asymptotic completeness, that is point number 2. Asymptotic completeness is equivalent to the following pair of statements. Is equivalent to the pair of statements that the wave operators omega plus minus AB are complete, and furthermore the singularly continuous spectrum of A is empty. which you can see from these definitions here. Here we have the addition that the singularly continuous part is vanishing, and then asymptotic completeness is equivalent exactly to these two statements. Furthermore, considering this here, we can say that we have the following implications. Asymptotic completeness then implies completeness. According to remark number 1. And of course, this implies weak completeness. This is clear because if both subspaces here are equal and are equal to HAC, then in particular they are equal, so we have weak completeness. Third remark, we will only deal with the notion of completeness henceforth. So to say, the third definition here is the important one for my lecture. And remark number 4. Let's come back to asymptotic completeness. Asymptotic completeness means that, and let's continue here. Asymptotic completeness means that H in plus HPP with respect to the operator A is equal to H out plus HPP with respect to A. And in other words, we can rewrite this identity in the following heuristic form. In other words, this means that the incoming states when you think of a scattering process plus the bound states which refer to this HPP space, this is equal to the outgoing states plus the bound states. And then remark 5, weak asymptotic completeness only means that the spaces of incoming and outgoing states are identical. Of incoming and outgoing states are identical. Okay, this is basically where we stopped last time, and today I would like to continue with the following remarkable result. First of all, let's have a look at this proposition. It is proposition 3.9 in my script, and it reads as follows. Let A and B be self-adjoint operators. Let A and B be self-adjoint operators. and assume that the wave operators exist. More precisely, I should say that the wave operators omega plus minus AB exist. Omega plus minus AB, which are defined as the strong limit that I told you right at the beginning, and assume that these limits here exist. Then we claim then omega plus minus AB are complete they are complete if and only if omega plus minus BA exist. And here I've changed the order. Yeah, at first sight, you might think, reading this proposition, that completeness is no harder to prove than existence. Yeah, because here completeness is derived from an existence result, but in fact completeness is much harder than existence in many cases. Yeah, nevertheless, this is an important result, and we should take the time to look at the proof. First of all, we assume that both omega plus minus AB and omega plus minus BA omega plus minus BA, and for the sake of completeness I will give you the definition once more. The strong limit for t to plus minus infinity exponential ITB exponential minus ITA, and the projection PAC with respect to A. We assume that they both exist. Yeah, and then I apply the chain rule, which we had last time. By the chain rule, this is proposition 3.6. We come to the following result. PAC of A, this is nothing but omega plus minus AA, simply from the definition of these wave operators. And now I can apply the chain rule to get that this is omega plus minus AB, omega plus minus BA. By the chain rule we find this, so that we can conclude that HAC of A is nothing but the range of PAC of A, or you can also write PAC of A applied to the whole Hilbert space H. We see that this must be contained in the range of omega plus minus AB. Yeah, which follows directly from this result here. Let's go on here. Now I apply proposition 3.4 that we also had last time. So in view of proposition 3.4, this proposition had three parts, and now I refer to the third part of this proposition, where we stated that h plus minus, which is the range, by definition, of omega plus minus of AB, that this is contained in h AC of A. Yeah, so that now you can put both results together, so that we conclude that h plus minus, in fact, must be equal to h AC of A, which follows from this result here and the result on the other blackboard. Yeah, and this shows then completeness. The other direction, conversely, suppose that omega plus minus AB exist and are complete. Then we want to show that also omega plus minus BA exist. And for this purpose, let phi be in HAC of A, which is, as I already said, the range of the projection PAC of A, or PAC of A applied to H. Now I use the assumption that omega plus minus AB are complete. So as omega plus minus of AB are complete, which means that the H plus equals the H minus, and this equals the HAC with respect to A, we find there is an element psi plus minus in the Hilbert space H, such that phi, which was an element of HAC of A, is equal to omega plus minus AB applied to psi plus minus. Yeah. This implies that we can consider the following norm difference. The norm of phi minus exponential ITA exponential minus ITB PAC with respect to B applied to psi plus minus, this has to converge to 0 when t goes to plus or minus infinity. Yeah, this follows simply from this equation here, and the fact that these omega plus minus are precisely the limits, the strong limits for t to infinity or minus infinity of this expression here on the right-hand side. Now I use that these groups here are unitary, so as exponential ITA and exponential minus ITB are unitary, we infer that the norm of exponential ITB, exponential minus ITA, applied to phi, minus PAC of B, applied to psi plus minus, that this must converge to 0. Yeah, but this shows that the limit for t to plus or minus infinity of exponential ITB exponential minus ITA phi exists. This is in fact already enough, because we only have to show that this strong limit exists. Furthermore, we get that it is equal to PAC of B applied to psi plus minus. And this completes the proof here. Yeah, what I said right at the beginning is my remark 3.10. Remark 3.10. At first sight, proposition 3.9 seems to say that completeness is no harder than existence. Yeah, but in fact, usually completeness is harder. So in fact, usually completeness is much harder. Okay. Now I would like to continue with Cook's method, and to understand the idea of this method, let's consider a very simple example from analysis to get the idea of this method. Assume that f, so let f be a C1 function on R. Let f be a C1 function on R with the property that the first order derivative f prime is in L1. Then we know that the limit for t to plus or minus infinity of f of t exists, which follows from this observation here. We can write the difference f of t minus f of s in the following way. We can write this as the absolute value of the integral over the derivative. So this is the absolute value of the integral ranging from t to s over f prime of u du. Yeah? And this can be estimated in the following way. We can estimate this by integral from t to s, absolute value f prime of u du. And this here converges to 0 when I send s and t to infinity, because of the fact that the first order derivative is an L1 function. Yeah, and this trick basically is adopted in Cook's method, which is used to prove the existence of omega plus minus. This is a very important and useful tool. And we will make use of this idea in the proof. So let's have a look at the theorem first of all. Let's do it here. It's my theorem 3.11. So theorem 3.11, which is Cook's method. And it reads as follows. Let AB be self-adjoint operators in the Hilbert space H with the property that the domain of A is equal to the domain of B. Furthermore, suppose that there is a set. Suppose that there is a set which I denote by D, and it's a subset of the domain of B, and the HAC of B space, which is dense, in HAC of B, and so that for any phi in D, there is a number T0, capital T0 in R, satisfying that the integral from T0 to infinity over the norm of B minus A exponential plus minus ITB phi integrated with respect to t is finite. Then this theorem says that the wave operators omega plus minus AB exist. So this is an existence result for the wave operators. And I think we will need the rest of the lecture today to understand the proof of this theorem. So let's start on the other blackboard with the proof. Proof. I have subdivided the proof into several steps to make it easier to read it. So first of all, let phi be an element of D and define eta of t as exponential ITA exponential minus ITB phi. Okay, my first goal is to show that this function eta is indeed differentiable and to compute the derivative. So we first show that eta is differentiable. And that its derivative, eta prime of t, is minus I exponential ITA b minus a exponential minus ITB phi. This is identity 3.5. Yeah, and first I would like to remark that as phi lies in the space D, which is subsets of the domain of B and the domain of A and also the HAC space. As phi is in D, we conclude that, of course, also exponential minus ITB phi is again in the domain of B and then also in the domain of A. Okay, now let's start. For U and V, real numbers, of course, U not equal to V and U fixed, we consider the following limit. We consider the limit as V goes to U of the following expression. Now let's begin here. I consider eta at V minus eta at U divided by V minus U. What is this? This is nothing but 1 over V minus U. And here I get the following difference, exponential I VB, VA, exponential minus I VB phi minus exponential I UA exponential minus I UB phi. This simply follows from the definition of the function eta. Okay, now let's compute this expression, in particular its limit. I can rewrite this first of all in the following way. 1 over V minus U, and here I get the difference, exponential IVA minus exponential IUA exponential minus IVB applied to phi plus exponential IUA exponential minus IVB minus exponential minus IUB applied to phi. Do you see this? Yeah, I've only added in 0 in the form of these two terms. Do you see this? I've only added in 0. And then we get this expression here. And this can also be rewritten in the following way. This is equal to 1 over V minus U. And here I get exponential IVA minus exponential IUA exponential minus IUB phi plus, these are 3 terms here, 1 over V minus U exponential IVA minus exponential IUA exponential minus IVB minus exponential minus IUB applied to phi plus a third term 1 over V minus U exponential IUA exponential minus IVB minus exponential minus IUB applied to phi. Yeah. Do you see what has happened? Yeah, the last term here is exactly this term here. So here nothing has changed. And concerning the first term here, you find that this is exactly the term which you get from here, exponential minus IVB multiplied with this factor here, and the other two terms again cancel out. So again, I've added in 0. Do you see this? Okay, so nothing has changed, basically. Now we can use theorem 2.2, which was basically Stone's theorem, or closely related to this theorem. So using theorem 2.2, we get that first of all, 1 over v minus u exponential IVA minus exponential IUA exponential minus IUB phi. This converges to I exponential IUA A exponential minus IUB when I send V to U. Yeah, this is exactly the first term in this decomposition that we have here. Yeah? And according to this theorem 2.2, we know that this converges to the limit here on the right-hand side. Okay, now let's check the behavior of the other two terms. Here we also find that 1 over v minus u exponential minus EIVB minus exponential minus IUB phi. This converges, again, according to this theorem, to minus IB exponential minus IUB phi when I send V to this fixed value u, so that in consequence 1 over v minus u exponential IUA exponential minus IVB minus exponential minus IUB phi, this converges to minus I exponential IUA B exponential minus IUB phi when I send V to U. Yeah, and if you look to the other blackboard, you see that this is exactly the behavior of this third term here. Yeah? So it remains to consider the term in the middle, the second term. So the second term in our decomposition may be rewritten as in the following way: 1 over v minus u exponential I VA minus exponential I UA applied to exponential minus I VB minus exponential minus I UB phi. Yeah, and then I can simply rewrite this in the following form. This is nothing but exponential I VA minus exponential I UA 1 over v minus u exponential minus I VB minus exponential minus I UB applied to phi. Yeah, but here we know that the first factor converges strongly to 0 when we send v to u. And we also know that the limit here on the right-hand side, the second factor, this limit, the strong limit exists. Yeah, so let me write this for short in the following way. This converges strongly to 0. And here we know that the strong limit is for v to u minus I exponential minus IUB b phi. Yeah, this exists. So that this second term here, in fact, converges to 0 when we send v to u. And if you look back to the other blackboard, we find out that the term here in the middle converges to 0 according to the observation on the other blackboard. And we have computed the limit of the first and the third term, which you can find on the other blackboard. Yeah, this is one of the limits here. And we also have computed one limit here. And now taking both results together, we find out that exactly what we need. Hence, we find that eta prime of t is exactly of the form I exponential ITA b minus a exponential minus ITB phi. So that 3.5 is indeed correct. So this achieves a proof. This achieves a proof of 3.5. Okay, let's go on step 2. We now claim that for all t bigger than s, bigger than t0, we have that the difference, the norm difference, eta of t minus eta of s, this can be estimated by the integral ranging from s to t over the norm of eta prime of u du, and we know that this object exists and we know how it looks like, and this is then equal to the integral from s to t norm b minus a exponential minus I bu du. Okay, let's consider this here. So for phi in the Hilbert space H, the map, the following map from R to C, which is given by t is sent to the scalar product eta of t with psi. This map is continuous and differentiable. Is continuous. Yeah, sorry, this should be psi here. For psi in the Hilbert space, this map here, I claim that it is continuous and differentiable. Is continuous and differentiable. And in view So in view of theorem 3.5, in view of formula 3.5, so we had in view of, formula 3.5, which was the derivative of this function eta, and the derivative of the map written down there is given by the following expression. So its derivative is given by the following expression, let's say d psi of t, which I define as the scalar product of b minus a exponential minus itb phi I times exponential minus ita applied to psi. Yeah, this is a simple consequence of the identity 3.5. And it's also clear that this expression depends continuously on t. So clearly, this expression depends continuously on t for psi in the domain of A, as we can write that d psi of t is nothing but, let's decompose it into two terms. Then we find that it's b exponential minus itb phi I exponential minus ita psi, and minus scalar product A exponential minus itb phi I exponential minus ita psi. And to make it totally clear, we can also rewrite this in the form that it is exponential minus itb. The order of these two operators, of course, can be exchanged in view of the spectral theorem phi. And here the second factor stays. And here we can throw the operator to the other side, use that it is self-adjoint, and again exchange the order of the two operators to obtain that this here is equal to exponential minus itb phi in the product with exponential minus ita a psi. And from this it is totally clear that this expression has to depend continuously on t. Okay, let's go on. So, in view of the fundamental theorem, in view of the fundamental theorem of calculus, we find that the scalar product of eta of t minus eta of s applied to phi times psi, this is then nothing but the integral from s to t over the derivative, and we have computed this expression here. This is nothing but the scalar product of b minus a exponential minus I ub phi I exponential minus I ua psi du. So this is standard. But now I use that the domain of A is dense. So as the domain of A is a dense subspace of H, we find that the norm of eta of t minus eta of s applied to phi is nothing but the supremum for psi in the norm smaller than 1 and psi in the domain of A, and the supremum over all differences, absolute value of eta of t minus eta of s applied to phi in the scalar product with psi. Yeah, this is a consequence of the fact that the domain is dense. So we can do this. And here on the right-hand side, we now can use this identity here so that we can estimate by supremum norm psi smaller than or equal to 1 and psi in the domain of A, integral from s to t, absolute value scalar product b minus a exponential minus iub phi and I exponential minus I ua psi du. And clearly this can now be estimated by the integral from s to t, norm b minus a exponential minus I ub phi du. Yeah, and this is what I wanted. So let's continue here. This achieves a proof of 3.6. Or maybe I have forgotten to give this number. So this achieves a proof of 3.6. Yeah, you can add this in your notes. 3.6 was exactly this estimate that this difference can be estimated in the following form. Yeah, you can simply add this if I have forgotten to give this number. Yeah, but what can we say now using 3.4? We infer that, this was the assumption in the theorem, we infer that the difference norm of eta of t minus eta of s phi, that this then converges to 0 when we send s and t to infinity. Yeah, but what does this mean? When we recall the definition of the map eta, hence, we conclude that the limit for t to infinity exponential ita exponential minus itb pac of b. Okay, this was not part of the definition of this map eta, but we said that the vector phi was in D, which was the domain of B in the intersection with the HAC space. Yeah, so we can add this here without changing something. Hence, this limit here exists. Hence, this limit exists for all phi in D. Okay, point number 3. Assume now that psi is in the orthogonal complement of HAC of B, which is equal to the orthogonal complement of D, script D, according to the fact that we had a dense subspace as D is dense. We, of course, find that exponential ITA, exponential minus ITB, and here we have this crucial projection, PACB, psi. This, of course, is 0, because psi is in the orthogonal complement. Yeah, and then, so clearly, so that the limit for t to infinity of exponential ITA, exponential minus ITB, PAC of B psi exists trivially. Yeah, let's sum up what we know up to now. We thus know that the limit t going to infinity, exponential ITA, exponential minus ITB, PAC of B, F exists for all F in a dense subset in D plus D perp. Yeah, and it's clear what we do now. So let now G be an element of the Hilbert space H and epsilon positive. Then we know there is an element F in D plus D perp such that the difference F minus G is smaller than epsilon because we have a dense subset here. And we write W of t, this should be exponential ITA, exponential minus ITB, PAC of B for t in R. Yeah, and we know that, thus, a simple argument now, the difference W of t, G, minus W of SG, this can be estimated in the following form. First of all, I'll write it down. This can be estimated by the norm of W of TF minus W of SF plus the norm of W of T F minus G plus the norm of W of S F minus G. And do you see this? Again, I've simply added in 0 twice. No? And then I have applied the triangle inequality. And this can now be estimated by, the first one remains the same. And then I get to epsilon. Because the norm difference of F and G is smaller than epsilon, and the norm of this operator W is smaller than 1. And then I get this. And this can then be estimated by 3 epsilon. Why? We do it here. this is smaller than 3 epsilon for large S and T. For S and T bigger than some T0 is, we know that the norm of W of T F minus W of S F goes to 0. This was the result of the previous step where we proved this for elements in this dense subset. And here I can exactly use now this result. So this goes to 0 for S and T to infinity. And this also finishes the proof here. In the next lecture, and to give an outlook to what we will do next time, we will apply Cook's method to the following pair of operators. A will be a Schrödinger operator, so it's minus Laplace plus a suitable potential, and B is the free Hamiltonian. Of course, both operators have to be defined so that they are self-adjoint operators in the Hilbert space, yeah, so that we have self-adjoint realizations of these objects here. And we will apply Cook's method to these operators acting in L2 of R3. And we will see that it will be crucial to obtain control on terms of the form absolute value of exponential I t Laplace phi of x. This will be clear in the next lecture when we go into the details, but let me state our result, proposition 3.12. Proposition 3.12, let H0 be the free Hamiltonian, which I define as always minus Laplace, and I restrict it to CC infinity of R3, and then I take the closure to obtain a self-adjoint operator, and let V be potential which is in L2 and which is also bounded. Yeah. And let then H be the operator H0 plus V, and then we also know that this Schrödinger operator is self-adjoint, so that H is self-adjoint. Yeah, of course, H0 is also self-adjoint, so let's state it here for the sake of completeness, so that H0 and H are self-adjoint with the property that the domain of H0, which is well known, is equal to the domain of H. Yeah, this follows, for example, from the Kato-Rellich perturbation theorem. Yeah, but what we actually want to say is then H0 is purely absolutely continuous. Then H0 is purely absolutely continuous, meaning that H AC of H0 is equal to the whole Hilbert space, and the wave operators and the wave operators. And you can imagine that this is of practical importance, omega plus minus HH0, which are the strong limits for t to plus or minus infinity of exponential ITH, exponential minus ITH0, and here I can, of course, leave away the projection because of the fact that H0 is purely absolutely continuous. So this projection operator in this case simply is the identity. So I can leave it away. And the wave operators exist. Here we will continue next time, and we will also discuss in the exercises the following lemma, which will be necessary to go through all this. I will state it here as our last lemma for today. This is an exercise. You will find it on the next sheet. Assume that H is a smooth function, let's say in Rd, for some d bigger or equal to 1, is real valued. Is real valued with non-vanishing gradient almost everywhere. Then the multiplication operator, MH associated with this function H in L2 of Rd has purely absolutely continuous spectrum. Has purely absolutely continuous spectrum. And you can imagine from this result that in particular, let's state this too here, in particular we find that keeping in mind what the Fourier transform is doing, any non-trivial self-adjoint differential operator in Rd with constant coefficients has purely absolutely continuous spectrum. And I already gave you the hint to work with the Fourier transform here, but all this will be part of the next exercise sheet, so the proof is an exercise for you for the next week. Okay, thank you for today. We now take a short break and then we continue with the exercise session. Thank you.